Okay, so now you're on page 110 and there's another problem just like the one on the bottom of page 109 that we just did together. So it says find all the real zeros. And you can try factoring, but it's really not going to get you anywhere. So your next best bet is use your rational zero theorem. And so we're going to make our list of our p's over our q's, like that. And then we could go through and do 12 divided by 10, which reduces to 6 over 5. And we could do synthetic division with 6 over 5, positive and negative. Or we can do 12 over 5 and 12 over 2, which is just 6, and 12 over 1, until we guess which one really works. Or you can smart kid cheat. You put this in the calculator, and once you put this in the calculator, you will get a graph that looks something like that. And you could try -1, and you don't want to guesstimate what that decimal is, so I wouldn't even bother with it, and I would try 2. And you're going to quickly find out that -1 probably doesn't work so nicely, but 2 works. So pause the video and start with 2 in synthetic division and see if you can find the other zeros, and then come back. So hopefully you got 2 to work out. So when you put 2 in the house for synthetic division, you should have gotten a remainder of 0, which means it works, leaving you with a quadratic, -10x squared minus 5x plus 6 equals 0. And I'm hoping that you're catching on to the idea that we're doing this until we get down to a quadratic. Because once we get down to a quadratic, we can do one of 2 things. We can factor it, or if we can't factor, we can always do the quadratic formula. And so that's what I did. I did the quadratic formula, and I got x equals 5 plus or minus the square root of 265 all over -20. So it said find all the real solutions, so I need 3 of them. My 2 is one of them. 5 plus the square root of 265 over -20 is another one. 5 minus the square root of 265 over -20 is the other one. Okay, so now we're going to go down here and talk about conjugate pairs. So we talked before about how if we had a plus bi to undo it, we were going to use the complex conjugate a minus bi. Well, see, no one really ever explained to you that this plus and minus up here is in the quadratic formula for a reason, and that's because these conjugate always come in pairs. There's always going to be an a plus version and an a minus version. So in other words, what we're saying is that if we tell you that a polynomial has a 0 of -2i, it must also have a 0 of positive 2i. Or if we tell you that 1 minus 3i is a 0, then you also have to have 1 plus 3i. So using that knowledge, it says find a 4th degree polynomial with real coefficients that has -1, -1, and 3i as the zeros. It's a 4th degree polynomial, but we only gave you 3 zeros, and that's because it's implied that -3i is also a 0. So we have x minus a -1, x minus a -1, x plus 3i, and x minus 3i. And this came from doing x minus -3i, then x minus my 3i. So there's my polynomial. I'm just going to clean it up a little bit. F of x equals, this is really like saying x plus 1 squared, and then x plus my 3i, and x minus my 3i, and just in case on the test, hint, hint, wink, wink, you're asked to do this, let's practice foiling it out. So x plus 1 squared is going to become x squared plus 2x plus 1. And then when you FOIL these two conjugates together, the middle should always go away. And so you should end up getting x squared plus 9. And now you would multiply these two together. So you're going to get x to the 4th plus 9x squared plus 2x to the 3rd plus 18x plus x squared plus 9. And if we were to clean it up and write our final answer, f of x would equal, I have an x to the 4th plus 2x cubed, 9x squared here, and one more there makes 10x squared, plus an 18x, and plus a 9. Okay, and then down at the bottom, it says that factors of a polynomial, every polynomial of degree n, where n is greater than 0 with real coefficients, can be written as a linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. So this means that what your goal is, and what I told you earlier up here, is that if you get it down to quadratic, you might be stuck, but you can't factor anymore, which is why you always have your wonderful quadratic formula. So now it says find all the zeros given that 1 plus 3i is a 0. So this is what we're going to do. If this is a 0, if 1 plus 3i is a 0, for example, let me do this. If I told you that x equals 6 is a 0, you would tell me that x minus 6 was a factor. So if I'm telling you that 1 plus 3i is a 0, then x minus that is a factor. And x minus 1 minus 3i also has to be a factor because these come in pairs. So now what we're going to do is I'm going to distribute this negative, so x minus 1 minus 3i. And I'm going to do the same thing here, x minus 1 plus 3i. And so now what I'm going to do is I'm going to FOIL these two things together. So x times x is x squared, x times negative 1 is negative x times 3i is plus 3ix, negative 1 times x is negative x, negative 1 times negative 1 is 1, negative 1 times 3i is negative 3i, negative 3i times x is negative 3ix, negative 3i times negative 1 is a positive 3i, negative 3i times a positive 3i, negative 3i times a positive 3i is going to be a negative 9i squared, and I squared becomes plus 9. And so now I'm just going to grab some colors really quick because things are going to cancel out. And that's the beauty of these conjugate pairs. So positive 3ix and negative 3ix cancel out. And this negative 3i and positive 3i cancel out. And if you multiply this together correctly, all the I stuff should go away. So now I'm left with x squared. I have a minus x here and a minus x here, so minus 2x. So I've done that one, I've done that one, I've done that one. I have a plus 1 and a plus 9, which gets me plus 10. And I know that you're sitting there thinking, Gidry, why are you doing all of this? Well, I'm doing all of this because this was a 0, which made both of these factors. And all I've done is taken two factors and multiplied them together. I haven't changed anything, but because I've taken these two factors and multiplied them together, I now have this quadratic, which was made up of factors. If these two are factors, then this itself is still a factor. And I'm going to use awesome long division to find the other two zeros, so I can solve this problem. So to make x squared look like x to the fourth, you have to multiply by an x squared. X squared times x squared is x to the fourth minus 2x to the third plus 10x squared. Subtract the whole thing. The 4's go away. This becomes a positive and a negative, so I'm going to have negative x to the third minus 4x squared. I'm going to drop down my 2x. So I need to multiply by a negative x. Subtract again. First ones always have to go away. Distribute this negative sign, negative 6x squared. That was a negative, it became positive, so plus 12x. Drop down my 60. Need to multiply by negative 6. Sorry, I should have dropped on negative 60. And then because these match, when you subtract, you get nothing, which is exactly what should have happened, because you should have gotten a remainder of 0 because this was made up of factors. So now all you're left to do is factor this. X squared minus x minus 6, which we know factors into x minus 3, and x plus 2. And now you have all of your zeros. It says find all of the zeros. Well, my zeros are x equals 1 plus or minus 3i, positive 3, and negative 2. And I promise you something like this is going to show up on your test. So make sure you can do a problem like this. Go back to Edmodo and there'll be one last video for you to watch.